Today, let's talk about soil redox, what it is and why it's important. It all starts with soil microbes. These microscopic little fellows come in many different forms and perform many essential functions. They play a huge role in the cycling of gases, for instance, pulling nitrogen out of the atmosphere and releasing carbon dioxide and methane back out. They also play a big role in plant growth and decomposition. Some microbes aid plants by fixing nitrogen from the atmosphere, which plants require to grow. Other microbes are pathogenic, making plants sick and even killing them. However, our main focus today will be on the microbes that specialize in breaking down organic matter, a crucial part of the cycling of various nutrients and gases. But where do these microbes get the energy to do this labor-intensive work? For that, we have to take a little detour into what are known as reduction-oxidation reactions, known simply as redox. Redox reactions are the basis for life on Earth. You can imagine here that we have two different beakers of molecules, each with their own electrons. We'll call the red molecules the oxidizers and the green molecules the reducers. Now, the electrons of the red oxidizing molecules are at a lower potential energy, while the electrons of the green reducing molecules are at a higher energy state. When allowed to react with each other, electrons will naturally flow from the higher potential to the lower potential, just like a ball down a hill. This difference in potential is what's known as the redox potential, which indicates just how strong the electrons are being pushed or pulled. The redox potential depends directly on the molecules involved and the energy states of their valence electrons. Microbes use redox reactions to get the energy they need to survive. For a decomposer in the soil, the oxidizer or electron receptor is one of a handful of molecular compounds present in the soil. The reducer or electron donor is organic matter such as dead plants. Not all oxidizers are created equal. The redox ladder illustrates which oxidizers can produce the most energy or pull on electrons the hardest. At the bottom, we have carbon dioxide and sulfate, which is most notable for the unpleasant sulfur odor commonly found in wetlands and coastal ecosystems. They can produce the least energy and are only used in anoxic or oxygenless environments. Next, the oxygen-scarce suboxic layer contains oxidizers such as nitrate, which can produce slightly higher potentials. None of them, though, can beat the redox king, oxygen. Due to its ability to produce high redox potentials, oxygen can be used to break down some of the toughest organic matter that doesn't normally get decomposed. Speaking of which, some organic matter is more easily decomposed than others. Fruit and leaves require fairly little energy to decompose, while wood is more recalcitrant or resistant to being decomposed. Charred organic matter such as charcoal is even harder to break down, remaining in the soil for thousands of years. After the redox reaction takes place and the microbe gets what it needs, we are left with the byproducts of decomposition. First, we have the resulting decomposed carbons, the compost. Most importantly, though, there are gas byproducts. Aerobic reactions will mainly produce carbon dioxide, while anaerobic reactions can also produce methane. These are both greenhouse gases, so it is crucial that we track how microbial activity changes as the Earth's climate and atmosphere rapidly change. Will rising temperatures affect the rate of decomposition? How do soil dynamics change as plants grow faster with enhanced carbon dioxide supply? Soil redox can provide a glimpse into this very complicated underground world.